All right, hi, and welcome to another video of mine. Today, we're going to be talking about my robot submitted for the NC Inspire CADathon, TSINC01. This robot somehow actually won that CADathon, um, which I'm pretty proud of. And so some people on Discord were asking me to make a video talking about some of the design and CAD techniques that I used while developing this robot. Um, so that's what I'm going to do. This video is going to be about the design of the robot, both some of the design features of it, but also the whys. So I'm going to be talking a little bit about the strategy, about what I do when I'm competing in a catathon, and about um, yeah, just really that entire all the like the mechanisms and what was driving a lot of the mechanisms on this. In another video, I think I'm gonna break down some of the different CAD techniques specifically that I use to make this robot, and some of the specific tricks in there and all that fun stuff. So, to start a little bit, start this off, I'd really like to talk a little bit about catathons as a concept. So, I've been participating in catathons since probably 2017 or so, really as a way to make myself a better mentor and to get myself better at CAD design. I'm not a professional mechanical engineer or draftsman, so I really need to whenever I'm helping students design robots, like it's important for me to get that experience so that I can help them do that better. Um, so that's why I do catathons. And to that end, I have some different rules and ideas that I kind of have about how I participate in them. For a really long time, I participated in the F4 catathon. Um, a few months ago, I joined the GDC for that. Um, which is a catathon that's really well known for emphasizing raw CAD over everything else, raw CAD and renders. Um, Personally, that's just not what I do. So um, I don't believe in designing a catathon robot that you can't build. I don't believe that's particularly good practice. And I don't really believe in CAD as anything other than being a tool for designing robots. Um, So one of my big rules when I'm participating in catathons is that I design robots that the team I'm working with can build. Um, that means I don't do fancy CNC stuff. That means that I put a lot more emphasis on designing mechanisms that would work over mechanisms that aren't necessarily cool. Um, so this one, I kind of put a threshold on it of like I wanted like a 95% real robot. Um, there's different like levels of this that I do. Like there have been catathons I've done that I participate and I go for a 100% real robot, which is exactly as 2220 would design it that year. So I've done ones on that where I just did a kit press drivetrain because that's what 2220 does right now is a kit of parts drivetrain, and that means that that's not necessarily going to rank high in a catathon, but I don't really care. Um, the point is to get better at the skills that I want to build. Um, my other big restriction on this catathon robot was no pneumatics at all. Um, that was kind of inspired by Team 148's robot this year, which had no pneumatics on it. Um, and I thought that was a really cool constraint to put on things, and really helped me explore some different ways of designing robots. Um, so to start off this, I think it's important to talk about like my strategic analysis of this game. Um, because my goal was a real robot, that means that I do a real strategy process, which I documented in both my technical binder here about the analysis on here. Um, and also, I actually did that ranking in my robot design sheet. So, where is it? Here. Um, so I do this. This is the same technique this is the same way that 2220 does our robot design process. So I think it's important to process that process it in the same way that you would break down and analyze a game in reality, because that's part of what makes you a better designer for FRC and just in general. Like, I think that the strategic design process in FRC is one of the most applicable things that you can take away from FRC when you go into a job, when you go into whether it's like an actual mechanical design job or software. Certainly, it's something that I found immensely valuable in my professional life. Um, so I really believe in doing that as part of this. Um, so some of the big parts of that that you can kind of see in here was number one, always drive, drive anywhere on the field, um, and be able to do that consistently and well. The number two thing on this was the climb. Climbing was really important in this game, and I think that a lot of people watching the stream didn't understand entirely how this game would be played in reality. Um, like the reality of this game is that scoring scrubbers is hard, is extremely hard. Um, and a lot of teams would not be very successful doing that. Um, Similarly, scoring pollutants was also really hard. Um, and I'm not sure if people just missed this or they willfully ignored it. Um, but pollutants leak in this game. That's a really cool game mechanic, and I really appreciate the InspireNC um, GDC for playing with that. But it made it really hard to justify building a pollutant focused robot in this game because your cycles, your alliance needs to be scoring more than 2 pollutants a second um, in order to keep up with the rate of return before you have a filter up. Um, and that is really hard. Like just flat out, like that is really, really hard. Um, you need to be, that means you need to be gathering those. That means you need to be, and you need to be scoring them, and you need to be doing that at a really, really fast rate. And it's really hard to maintain that. So one of the key insights, and that was talking, I mean, I had a lot of really public discussions with people on the FRC Discord about this game, which informed my strategy is like scoring scrubbers is hard, pollutants are hard, but you need scrubbers to make pollutants worth it, right? So, and like if you look at most games in FRC, teams typically struggle to score more than like 4 cycles in a match, right? So when you look at like a filter and trying to score 9 of those scrubbers, you you're talking about 2 plus average robots for an entire match to get a single filter. And in that time, like if you're scoring pollutants, yeah, you're bringing them over to your side of the field, but they're leaking and they're leaking fast. Um, so this all makes the climb even more important because if you can get those 30 climb points, like that's huge. Like that's the way I would expect this game as it's played in actual FRC is that this is like an even worse version of 2017's climb roulette. Um, it's just climbs are king, and you got to get scrubbers in, and maybe you get some pollutants in at the end of the match. Um, so that informed this strategy list, which is basically focus on scrubbers, focus on climbing at the end, and if you can, get some pollutants in. So this entire robot was designed with those things first in mind. Um, so big parts of that informed this design is so first this drivetrain. We'll talk about this drivetrain first. So this drivetrain is kind of the four rail architecture that has been becoming a lot more popular in recent years. So it's designed to have a battery back here. Um, we've got some single speed gearboxes and some 3.25-inch wheels. In the vast majority of FRC games, wheels this small are a bad idea. But this is a true flat field game, which means that that is acceptable. 3 and 1/4 inch wheels are an acceptable thing in my mind for this game because the field is so flat. You bump that up to 4 inch wheels. Honestly, that's probably safer. Like as I was designing this, I kind of considered bumping it up just because people are doing partner climbs, and that's probably a good idea because it makes partner climbs bigger. But I just stuck with the 3 and 1/4 inch wheels, partially because I haven't really designed many robots like that. And catathons are about growth. One of the other big things you'll notice in here is we've got the PDP really close to the battery. This is a really good design feature. We've got VRM down here and not a whole lot else. Like there, a lot of the electronics on this are the motor controllers that are out close to their motors because they're Spark Maxes, and you want to keep those within the 12-inch wire length coming off of those of the motors that they drive. Um, or we've got like the radio up here. Like that's there's just not a whole lot of electronics on here, and I think in the future how I'll advise my team is like it's great to avoid pneumatics. Like it just simplifies everything. Um, One of the other big things you'll notice throughout this entire design is that there are a lot of places where people would add lightning holes that I didn't. And the reason for that is this. So let's take a look at the weight of this robot. Uh, this robot, as is, weighs, drumroll please for on-chip's mass calculation, which is apparently still figuring its life out. We'll wait for that. But I'll tell you right now, it's about like 115 pounds, um, as is just like the whole base robot, or 110 pounds. I guess I'm was a little bit off, right? So this whole thing's 110 pounds, but there's something a little bit funky about this. Where are most of those pounds? Let's look at that drivetrain. The drivetrain on this robot is like, I think it was around 50 pounds, um, which is a really heavy drivetrain. And it's heavy because I added steel weights down there. This robot is super light. Like, this is one of the lightest robots I've ever designed. Um, and really intentionally so. Like, this is 16th inch on the elevator. There's a lot of polycarb on this robot. Um, and that lets us keep the center of gravity really, really low. It lets us keep that center of gravity down to like, I think in this lower position, the center of gravity is like 10 inches off the ground, maybe less. Maybe I think it was like 9.5. I'm not going to make you sit through on-shapes mass calculation for that because apparently it's really slow right now. And that's a really good thing for being able to drive around, drive quickly, and operate with this elevator. Uh, so let's talk about the scrubber next. So the scrubber and the climb. So this, what I called the carriage manipulator because it's mounted to the carriage, integrates a lot of key functions of this robot. So it integrates the scrubber claw, which has some really cool design features of it that I learned a lot just designing it. Um, so it includes this kind of finger construction, which is, I don't know, I think it's really cool. I've never done something like that, so it was a really cool way to integrate that in a really light and fastenerless way. So this entire thing is held together by these tube nuts, which keep this in position, and this entire thing is just here to center that scrubber when it's in position. Um, in this lower position, when it's and this motion is apparently just not, it's kind of working. So basically, it's like this position, except for all the way at the bottom, puts this at about 18 inches and right at the edge of the bumper frame perimeter. That's very intentional. That was a really intentional choice to make it super easy to grab from the loading stations with minimal movement. So this robot can operate just a lot of the match at its lowest position with a super low center of gravity. which is very intentional. This, yeah, the scrubber claw, yeah, like I said, it has this self-centering thing right here. It has something that you'll notice throughout this entire robot if you dig into it, which is this gear reversal right here. Um, So what that is basically I didn't want to use more than one motor, but I did want these to run in opposite directions. So you can do that a couple of ways. You can do that with what's called an infinity belt, which is basically you take a piece of poly belt and you twist it in a figure eight. Um, I did this as a gear thing, so a gear reversal. So when you take a gear and you run it, against another gear, the direction reverses. So we use that. I use that here. And then I also use that a lot of places around here to do that. So I use that in what, 4 places? Yeah, here, a couple times on there, and then in a kind of different way here, which is, um, I don't know, I'm really a fan of the way of doing that. It's a little bit heavier than the Infinity Belt, but it means less slip, which is kind of nice. Um, So, like I said, the overall concept of this robot was I don't expect to be doing very much with pollutants. Um, but what I do expect to do with them is score them really, really fast at the end. So this is designed to be a dumper robot. What that means is that in its extended position, uh, this ends up right up against the field, right up at that thing, and just whatever the linear speed on this is like 30 feet per second. So it'll just shoot those all into there. um, which was, I don't know, it was fun thinking up that design, and it turned out to be a pretty unique one. Um, the thing I'm least comfortable about with this entire manipulator is actually its climb. Um, this climb is based around the idea that the ring that you're hanging from, for context, do I have the field? Hopefully this won't take too long to upload. Um, the ring that you hang from is actually on rope in this game. So this is in CAD, but these are ropes, these 2 bars here, which means that it can move a bit. It means that, and you can kind of see this is off. I can't really move it well. But the entire idea behind this was we'd lift up and run these belts backwards and hook this over that. Um, and this hook, when you came back down, would end up grabbing onto that. I'm not entirely sure how well this would work. It's, yeah, the least comforting part of this robot. I think it probably could have done with some guides. Um, and this is something I'm going to be doing throughout this, right? Is talking about where I'd improve stuff. Um, yeah, I would probably add some guides on there just to make this a little bit better. But you can kind of see, geez, it's taking a while to load in. In our highest position, come on, I believe in you, maybe not. But you can see it has like another foot or so you can easily get up to that position. Um, so that's kind of how that was designed. The 24-inch, so these are 24 inches apart. So the 24-inch speed, which is another thing I designed this for, is like half a second or something, which is nice and low. So we got this. This entire pollutant path is just, it's designed to have zero indexing and zero, like, the goal of this is to vomit balls really, really fast. So they don't need to be super organized. They just need to be in this, and then they need to go really fast out of it. And that's how this entire thing is designed, is just there are no constricting points, which means there's a lower propensity for jams. So just feed directly into there. feed directly into that in this kind of pseudo pass-through thing. This makes use of an asymmetric 4-bar, which is hard to see here, but I'm a big fan of those. That lets us take it all the way in. One of the things that I probably would have done if I had thought through this a little bit more is this can actually extend further back. And extending further back would let me put a beater bar out here, which would be a good thing. I'm a little bit concerned about this intake as it is. I'm pretty sure it would work just because it's all polycarb, and like polycarb is pretty durable, but mildly concerning. Talk about some of these joints. So one of the big things when you design arms is that you want equal force on either side, because otherwise you get sag. So in this case, we have it pulley driven on this side, which goes out to here. And then we have another one on this side, which helps us keep this all level. You'll notice a similar thing over here. This gear on each side to help make sure that this doesn't sag. This probably wouldn't have, just because it's all so much aluminum, but I did that anyways because it's a good practice. You can kind of see the reversal bit that I do up here, which is a really nice way to get that nice and close. This elevator is hilariously overpowered, and yet still also probably a little bit too slow. If I had taken a little bit more time with the elevator, what I probably would have done is bumped these teeth up a little bit and swapped this out for a steel bolt gear, because I definitely had the weight, and that was that just would have been a good call. The biggest design mistake on this robot is probably this rigging. I'm not confident that this rigging would actually work in reality. Like, it's just really tight around this, and I probably would have. What I wanted to do, like a little bit into this, was redesign this to do an internal belt rigging, like 2010's 2018 robot. All right, so that's about the design of this robot. In another video, I will talk a little bit about some of the CAD techniques about it.